to the next one. Acha, let's look at this now. Find the number of different arrangements of the 9 letters in the word attentive in which the 2 E's are together, but the 3 E's are not all together. Okay, now 2 E's should be together, but the T's should not all be together. Now, what does that mean? There are 3 T's in total, 1, 2, 3. Not all together means this case is not allowed where all of them are together. However, 2 together and 1 separate, that is fine. And all of them separated, that is also fine. Okay? Walaikum assalam, Musa. Okay, so can we use the dashes and stars method in this? Can we use the dashes and stars method? Will that work? That method separates all objects of a particular type. Now, we don't want to separate all objects in this case. We only want to separate, only want to exclude the case where all of them are together. So in this case, we would have to use the method in which we have total minus together. Now, for the total arrangements, however, this is an important point in this. You see, the 2 E's, they have to be together in any case. The 2 E's, in either case, they have to be next to each other. They have to be together. Okay? So the total case that we consider, that would be total arrangements with E's together and no condition on the T's. Subtract from that the arrangements with the 2 E's together, and not all, or you can say all T's together. When we subtract these two numbers, that will give us the case where the 2 E's are together and the all T's are not together. T's are not all together. Okay, so total minus together method, that is what we are going to use here. Now, how can we do that? There are 9 letters in total. So what we can do is we can start with 9 boxes like this. We've got these 9 boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9. These are 9 boxes that we've got. We want E's to be together. We can merge 2 boxes and we can put the 2 E's in that merged box. Okay. Now, there are 8 boxes in total. 7 letters in the remaining boxes. What are those letters? A, T, T, N, T, I, V. In how many ways can we arrange these boxes now? All of these letters now, there are 8 boxes in total, so we have 8 factorial from that. And then in those 8 boxes, there are 3 T's that are identical. So what we do is we divide by 3 factorial because of that, because of the 3 T's that we have got. So it becomes 8 factorial over 3 factorial. That's the total arrangements in which the 2 E's are together and there's no other condition. Now, subtract from this the case where all the E's are together and all the T's are also together. Let's do that here. I just copied that. Now, again, what we have is 9 boxes initially. We merge the 2 boxes for E's, and then we merge another 3 boxes in which we put 3 T's. What are the remaining letters? The remaining letters are A, N, I, V, which are all different. How many boxes do we have now? 6 boxes. And how many ways can we arrange 6 boxes? 6 factorial. And all of these boxes are different. So we just have 6 factorial. We don't divide by anything, and that will give us the result. So you're saying the first one gives us 6720. and the second one 720. And that gives you the result, which is 6,000, and that's your final answer. That's the second twist. Make sense, right? Okay. Again, not that complicated. Not that complicated. Achha. Let me quickly put the paper link in the description here as well. Just give me a second. Where was the paper? Share. Mohit, if you're not interested in the paper, you can do something else. But please don't distract everyone else as well. Achha, I'm leaving the paper link in the group description. Yes, Mohit, you've said that to me, I don't know how many times now. March 2026, paper 5.2. Okay, I've added the paper link in the description. I'm going to post that here as well. Okay, sure. Let's look at the next part now. Let's look at the next part, part B. Find the number of different arrangements of the 9 letters in the word attentive, in which there are at least 4 letters between the two E's. At least 4 letters between the two E's. Now, this is a standard question that you keep seeing in recent papers, right? That you have a certain number of letters between two given letters. But the additional complication here is they've not specified how many letters are between the two E's. There are at least 4 letters. That means it could be 4 letters between the two E's. It could be 5 letters. It could be 6 letters, right? So you'll have to consider multiple cases for this. Let's consider what could be the possible cases that we get. Now, at least 4 letters means 4, 5, 6, and so on. Let's start with 4 first of all. So what we can do is we can say initially, we have these 9 boxes. We have 9 boxes like this. We are considering our first case in which there are 4 letters between the two E's. So 2 E's and 4 other letters. How many letters will that become? 6 letters in total. So we can make a big box that has 6 letters in it. 1, 2, 3, 4, 5, 6. This is a big red box. Now, this red box has 6 letters in it. Okay. Now, on one end, we have an E. On the other end, we have another E. Between these two E's, we have other letters. Now, what's the number of possible arrangements that you can get in this case? This red box, it could either stay in its current position or it can go here or here or here. There are 4 possible positions for this big box. So we can say there are 4 possible positions that this big box can be in. Okay, now what about the remaining letters? The remaining letters that we are left with apart from the E's, how many are they? A, T, T, N, T, I, V. These are the remaining letters. There are 7 of them. And we have 7 remaining boxes, 1, 2, 3, 4, 5, 6, 7. There's no condition on the remaining letters. They can go anywhere in these positions now. Okay. So we can say 7 factorial. However, how many of them are identical? There are 3 T's in them. We divide by 3 factorial because of that. And that gives us the number of possible arrangements in the first case. You can see what that is. 3360. That's your first possible case in which there are exactly 4 letters between the two E's. Okay, there are exactly 4 letters between the two E's in this case. Makes sense? Why not use factorial? Because just 4 is inefficient in some cases, I remember. That was when you had some condition on the remaining letters as well, right? We did a couple of examples on that, at least one example in the last week, if you remember. But in this case, there's no condition on the other letters, so it'll be easier to just use this method. This was the standard method that we used to use, right? So there's no condition on the remaining letters, right? So in this case, this is going to be very easy to understand. This was the first case, exactly 4 letters between the two E's. Then we have the second case. Now, if you understand the pattern, you can actually do it without making other diagrams as well if you think about it. If you think about it, when we have 5 letters between the two boxes, between the two E's, the only thing that is going to change now is, let me show that to you for this one case at least. The only thing that changes now is this red box becomes bigger. So now there are 7 letters in this red box. There are 2 E's at the two ends. Now this red box can go in 2 other positions. So one, its current position, and 2 other positions, that will become 3 possible positions. But for the remaining letters, we still have 5 and 2 more, 7 positions. For the remaining letters, we are still going to have 7 factorial over 3 factorial. And that will give you some number. You can see what this number is. 2520. This is 2520. Now, do you understand the pattern? 7 factorial over 3 factorial, 7 factorial over 3 factorial. This is going to remain the same. This is not going to change. So in the next case, when we have 6 letters between the two E's, the only thing that changes is this number is going to change to 2. And in the next case, this outside number, there will be nothing outside. It will just remain 1. So we have 4 cases. One case in which we have 4 letters between, another case in which we have 3 letters and then 2 letters and then 1 letter and then no letter. I'm sorry, the other way around. The first case is when you have 4 letters between the two E's and then 5 and then 6 and then 7. These are the possible cases that we've got. So you do not even need to show the other cases now. You could say the first is this number. The second is this number. If you follow the same pattern now, the next case is going to be 2 into 7 factorial over 3 factorial. And then the last case, that will just be 1 into 7 factorial over 3 factorial. What are these numbers? 1680 and then the next one 840. These are the 4 possible cases that we've got. You add up all of them and that will give you the result. So the final result is going to be 3360 plus 2520 plus 1680 plus 840. You can see what that turns out to be. What did they ask for? The number of different arrangements of these letters. Given that condition, you can see what that turns out to be. That's 8400 in total. 8400. That's your final answer. Does that make sense to everyone? Any issues with this? Any problems with this? Okay, Rita, what was your method? What were you trying to do there? 4 factorial. Why are you doing 4 factorial? Why are you doing 4 factorial? No, but why 4 into 3 into 2 into 1? Where are 3, 2, and 1 coming from? We have one box. This is one box. And it can come in 4 possible positions. Acha. Okay. So you're saying you're combining all the cases? You're combining all of these cases? And by combining them, you're saying we can write it as 4 factorial? because it's 4, 3, 2, and 1. We are adding these cases, right? We're doing plus, plus, plus. In factorial, we multiply, right? So that's something totally different that you're doing in that case. ठीक है? Makes sense? This was a bit tricky. If you've come across these questions, if you've practiced these questions before in the past papers, that it'll make a lot more sense. But that's how you'd approach it. ठीक है? चलें. Yeah, so generally, when they give something like this, at least a certain number of something, at most a certain number of something, that is a hint for you that you will need to make cases, right? Because it will be very hard to do it in one single line in that case, because at least means there are going to be multiple possibilities. Okay, you have to consider those multiple possibilities by making cases like this. Okay. Acha, chale. Let's move on to the next one. This was part B of this. Question number 2. What we're doing in both of them. Acha, how many different arrangements of the 8 athletes are there in which there are at least two athletes between any two hurdlers? Okay. 8 athletes, that's the total number of athletes that we've got. 1 sprinter, 3 hurdlers, and 4 throwers. Okay. We've got 1 sprinter, 3 hurdlers, and 4 throwers. These are the 8 people that we've got. Now, if they want at least 2 athletes between any 2 hurdlers, and there are 3 of them, let's consider the possible scenarios we've got. There are 8 people in total, right? That's a different kind of condition. We haven't seen something like this before. I have to think about it. We have 8 places initially, right? Now, what is it that they want? Between any 2 hurdlers, there should be at least 2 other athletes. Actually, there's no condition on the remaining people, right? So we can club the remaining people. There's no condition on throwers and sprinters, right? So let's just say there are 5 other athletes. So there are 3 hurdlers and 5 non-hurdlers, right? We don't care who they are. They're just other people, right? Apart from those 3 hurdlers. Now, if we want at least two other athletes between the 2 hurdlers, we could think of it like this. We could have an H in the beginning. Let's consider this scenario. We could have an H here. Let's call this H1, H2, and we could have an H here. This way, we have at least 2 other athletes between every 2 hurdlers. This is one possible scenario. Can we find the number of possible arrangements for this scenario? What would be the number of possible arrangements for this? Hurdlers, they can be arranged in 3 factorial ways. They can switch places, right? H1, H2, and H3. And the remaining 5 athletes, they have 5 places for them. 1, 2, 3, 4, 5. They could go in those 5 places. That's 5 factorial. For this one particular case in which what we have fixed is that there should be 1 hurdler in this position. This position of the hurdler is fixed. Another hurdler in this position. And another hurdler in this position. We have fixed the positions. This is one possible scenario. Now, how many possible positions can be there for the hurdlers that satisfy the condition given? This is one possible position, right? Another possibility could be that we have something like this. 1 hurdler here, another hurdler here, and another hurdler at the end. That would also satisfy the condition, right? We have 2 boxes here, and then 3 boxes here. You have at least 2 other athletes between the 2 hurdlers. This could be another possible scenario, right? Let's call this the second possible scenario. What other possibility is there? We could say there is one hurdler here, another hurdler here, another hurdler here. That's another possible scenario, such that we have 2 here and then 3 here. In this case, we've got 3 here and 2 here. This also satisfies the condition. Okay. And then, is there any other possible case? We could have one hurdler here and then 2 people here, another hurdler here, 2 people here, 2 other people, and then another hurdler here. This is another possible scenario. And that's it, right? There's no other possible case. These are 4 possible cases, and each of them would have the same number of possible arrangements. 3 factorial into 5 factorial. 3 factorial for the hurdlers, 5 factorial for the remaining 5 people. So there are 4 cases like this. We can say 3 factorial into 5 factorial plus 3 factorial into 5 factorial plus 3 factorial into 5 factorial plus 3 factorial into 5 factorial. That's the same thing as saying this whole thing multiplied by 4. And that will give you the result. Is that okay? These are 4 possible cases that we can have. And that gives us 2880. And that's our final answer. Now, I'm not sure what you mean by that. Yeah, this was not very difficult as well, but it was not one of those standard questions that we see on permutations and combinations. So it required you to think. Let's figure out. Find the number of different arrangements of the 10 letters of the word zoological in which the 3 O's are together and the 2 L's are not next to each other. Now, that's a standard method that we study when we do arrangements. Some objects need to be together and some other objects should be separated. How do we think about this? The 2 L's should not be next to each other. So what we can do is, we can say there are 2 L's, and then the rest of the letters, let's call them other letters. Okay. Remaining letters that we do not have to separate. How many are they? There are 8 of them. Now we start from the objects that we need to separate. We start from the objects that we do not need to separate. Okay, we start from the objects that we do not need to separate. These letters we do not need to separate, and we make dashes for them. 1, 2, 3, 4, 5, 6, 7, 8. We make 8 dashes for the remaining 8 letters apart from the 2 L's. Okay? But there's a condition. The 3 O's must be together. So what we do for that is we merge 3 dashes. We merge 3 dashes. Merge 3 dashes and make a single big dash here and put 3 O's on that 1 dash. That will make sure that the 3 O's come together. And now the remaining letters, what are they? We've got Z and we have G, I, C, and A. These are the remaining letters. Okay? In the gaps between these dashes, we can place these L's that we have to separate. So L's could come in these places. 1, 2, 3, 4, 5, 6, 7. These are the possible positions for the L's. Okay. Now let's do arrangements. How many possible arrangements do we have for these dashes? There are 6 dashes, right? We can arrange them in 6 factorial ways. All of them are different. These O's, do their arrangements matter? No, we don't have to arrange them. Even if we do arrange them, we could say, okay, there are 3 O's, so 3 factorial, but all of them are identical, so divide by 3 factorial. So arrangements for O's, they don't matter. That does not matter, right? Then what about the 2 L's? The 2 L's can come in these positions, 1, 2, 3, 4, 5, 6, 7. There are 7 possible positions for the 2 L's. We could say that will become 7p2. Arrange those two L's in these 7 positions. However, the two L's are identical, so we divide by 2 factorial. And that should give us the result. You can see what that is. 15120, that's your final answer. Okay. Don't we consider the placement of the Oswala box? We're already considering that. When we do 6 factorial, this box is already included in that, right? 1, 2, 3, 4, 5, 6. There are 6 dashes. That's why we have 6 factorial. We are already considering that. Okay. All right, let's move on. That was part A. Find the number of different arrangements of the 10 letters in this word in which there are exactly 5 letters between the two L's. Again, that's a standard question as well. We see this repeatedly in recent papers. We could say there are 10 letters initially. So we have got 10 boxes for those 10 letters. We've got 10 boxes for the 10 letters. There are exactly 5 letters between the two L's. So 2 L's and 5 other letters. How many total letters does that become? 7 letters. So we have a big box that has 7 letters in it. So we have this big box. We have this big box that has 7 letters in it. On one side of this big box, we've got an L. On the other side as well, we've got an L. Okay. Now, what are the possible positions of this red box? It could come in its current position. It could come here, here, or here. There are 4 possible positions, right? So its current position or this, that's 2, 3, and 4. There are 4 possible positions of that big box. So we have 4 for that, right? For this one box, we have 4 possible positions. Then what about these two L's that we've got? They can switch places. Does that matter? They're both identical. So them switching places, it does not matter. What about the remaining letters now? Apart from the two L's, we've got now 1, 2, 3, 4, 5, and then 6, 7, 8. 8 places left and 8 letters. That will be 8 factorial, in which we can use, and we can arrange 8 letters in 8 letters in 8 places. However, 3 of them are identical. We have to divide by 3 factorial because of that, because 3 are identical, that 3 O's are identical. And that will give us the result. You can see what that is. 26880, that's the final answer that we get. Right? This is again a standard question that we've done many times before as well. In recent papers, it comes again and again. In all the recent papers, actually, in every session, you'll find this question. Okay. Let's look at the next one. Now they're saying 2 letters are chosen at random from the 10 letters in the word zoological. Find the probability that these 2 letters are different. Okay, now that looks a bit tricky. That looks a bit tricky. 2 letters are chosen from the 10 letters. Find the probability that the 2 letters chosen are different. Okay. How do we think about this? Since we're only choosing 2 letters, we could also think of a tree diagram, I think. That will also work. Or we could make cases. Let me think about it. Remember what we generally do in such problems? When we have repeated letters and we have combinations involved. We need to make cases for the repeated letters, right? What are the repeated letters? There are O's and L's. O's are repeated and L's are repeated. So let's make cases for the repeated letters. Let's do it the standard way. O, L, and then the remaining letters are not repeated. The remaining letters are Z, G, I, C, A. These are 5. O's are 3 in number, L's are 2 in number, and the remaining letters are 5 in number. That makes it 10 letters in total. Now, if the two letters must be different, what are the possible cases that we can have? One possibility is that out of the 3 O's, we select 1, and out of the 2 L's, we select 1, and out of the remaining 5 letters, we select 0. That's 1, 1, 0. That's one possibility. Another possibility could be we have 1 O, 0 L, and 1 from the other letters. 1, 0, 1. Then we could have 0 O and then 1 L and one other letter. Okay. Do we have another possibility? Do we have another possibility? Are these the only cases, or would we have another case as well? 0, 0, 1, 0, 0, 1, or 0, 0, 2? 0, 0, 2. That both letters are selected from these 5, right? Because they're already different. So if both of the letters are from these 5, they would be different from each other. These are the 4 possible cases that we end up getting from this. Now, what about the probability then? What is the probability going to be? Number of favorable outcomes, we'll talk about that, divided by the total number of possible outcomes. There are 10 letters in total. We have to select 2. 10C2 is going to be the denominator. What about the numerator? Remember, this is that case in which we are finding probability, and we have combinations, and we have repeated letters. What did we use to do in such problems? Repeated letters, probability, combinations. We had to treat each letter as different. When we are looking for probability, when you're finding probability in a combinations problem, when you have repeated objects, you have to treat every letter as different, every object as different when you're finding probability, right? In number of selections, we consider them same. In probability, we have to consider them different. We spent time understanding the logic behind it, but then you have to memorize this condition. Probability, combinations, identical objects. When it comes to probability, you have to treat the objects as different in combinations. Now, let's go back there. So we will have to select from the 3 O's and the 2 L's and these letters as well. The first case, what does that become? 3C1 into 2C1 into 5C0. The second case, 3C1 into 2C0 into 5C1. 3C0 into 2C1 into 5C1. And then finally, 3C0 into 2C0 into 5C2. Now let me just confirm all of them. 3C1, 2C1, 5C0, 3120, 513021, 51, and then finally 0, 0, and 2. Okay. What do we get from this? The first one, 3 into 2, that is 6. The second one, 3 into 1 into 5, that will be 15. Third one, 1 into 2 into 5, that will be 10. The fourth one, 1 into 1 into 10, that will be 10. Add up all of these numbers. You get 35 plus 6, which is 41, right? Yeah, 41. And that will give you the result 41 over 10C2. You can see what that is. What's the probability? 41 over 45. That is our final result. Okay, that's what we were looking for. Makes sense to everyone? Now, this is the standard method that we use for such problems. Combinations, repeated letters, we make cases like these. In this case, since we just were selecting two letters, tree diagram would also not be very complicated because we're just selecting two letters, right? We could say in the first case, we could have L or an O or some other letter. Let's call that X. Then in the second step, O, L, X, O, L, X. X means remaining letters. O, L, X. We can only do this because we're just selecting two letters. If it was more than two letters, you can see how big the tree diagram would become, and then it will not be very efficient anymore. But in this case, since we're just like selecting two letters, it'll just be two steps in the tree diagram. This will be pretty efficient as well. The first time you select an O, what's the probability? 3 out of 10. L, 2 out of 10. Remaining letters, 5 out of 10. The second time you select an O, if you already selected O the first time, it'll be 2 out of 10, 2 out of 9, sorry. Then 2 out of 9 and 5 out of 9. And then similarly here, after L, 2 out of 10, you got 1 out of 9 here, and 3 out of 9 here, 5 out of 9 here. If you selected one of the other letters earlier, this will be 4 out of 9, and the others will be 3 out of 9 and 2 out of 9. And what are the possible cases in which you get different letters? O, L, O, X. Or you could actually also do this. Subtract from 1 these cases, OO and LL. And in all the other cases, you'll have different letters, right? And that will give you the result as well. I think it should give you the correct result. I'll just try that quickly. OO and LL. We are not missing any cases, right? LO, LX, all the rest of them are all different. XO is different, XL is different, XX is also different, right? No, XS is not the same, right? Because in the remaining letters, all letters are different. So if you're selecting Z the first time, Z cannot come again. So that is also different. So identical are only these two cases. We can do 1 minus 3 out of 10 into 2 out of 9. And also 2 out of 10 and 1 out of 9. And that gives us 41 over 45, the same result as before. Okay. So 1 minus 3 over 10 into 2 over 9. Also minus 2 over 10 into 1 over 9. And that is going to give you 41 over 45. Mostly this is not efficient in such questions. In most cases, it's not efficient in such problems. In this case, since we are only selecting two letters, there are only two steps in this tree diagram. If there was even one more step after this, if we were selecting three letters, for instance, in the next step, it will become 27 branches. And that becomes too big. So it would not be very efficient anymore. And in most questions that you'll find like this, they ask you to select more than two letters. So this would be the more appropriate method for most such problems. If they asked you for number of selections, then we do not select from O and L. Then we do not select from them. Then we only then we get rid of this part. This is not going to be there because then O's will be identical, L's will be identical. We would only be selecting from the remaining letters. Yes. Is that okay? If we were just finding the number of possible selections, we would get rid of this part. Number of possible selections that satisfy this condition, that will be given by this. 5C0, that's 1 plus 5, which is 6. 6 plus 5, that is 11. 11 plus 10, that is 21. You get 21 from that. Okay? All right. 10 letters in this word. 10 factorial divided by. Are there any repetitions? S, S, and that's it. 2 factorial. And then E, 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 3 factorial. Are there any other repetitions? Y, C, H, L. There are 2 L's as well. We divide by 2 factorial as well. Okay, and that will give the result. You can see what that is. It's a country. Seriously. 151200. It must be some state or a city, I think. Country का तो सुना होना चाहिए था फिर. हो सके. 151200. Okay. Acha, let's look at part B now. Part B. Oh, okay, I was expecting you to be focusing on the class right now. I did not expect that you were searching for something else, but that's okay. How many different arrangements are there of the 10 letters in this word, in which there are exactly 2 letters between the 2 S's and one of these 2 letters is C? Okay, how do we think about this now? One of those 2 letters that is there inside, that has to be a C. Now, let's make this box like this. There is a total of 10 letters, right? There's a total of 10 letters. We can say we've got these 10 boxes. Now, between the 2 S's, there are 2 other letters. How many letters does that become in total? One S on one side, another S on the other side. And then between them, you have 2 other letters. We can say there's one big box of 4 letters. And this one big box, on one side, you have one S. And on the other side, you have another S. This is one big box. Okay. What are the remaining letters now? The remaining letters are S. No, the S are already counted there. E, Y, C, H, E, L, L, E. These are the remaining letters. But C has to come in one of these 2 places. C has to come in one of those 2 places. Now, how do we think about this? We've got this one big box. And then we have 1, 2, 3, 4, 5, 6. 6 other boxes. What's the total number of big boxes that we've got? 1, 2, 3, 4, 5, 6, 7. These are 7 boxes in total. In how many ways can we arrange these 7 big boxes? We can arrange the 7 big boxes in 7 factorial ways. We can arrange them in 7 factorial ways. Okay. Now, once we have arranged these 7 big boxes, how many of them are identical? 2 boxes will have L's in them. So we divide by 2 factorial because of that. Three of those boxes would have e's in them. We divide by 3 factorial because of that. So we would have handled these outer 7 boxes. Okay. Acha, this is one way of doing this. This is one way of doing this. Since we have a condition inside, I'm using the other method. Remember, we discussed two methods for this. S1, permutations and combinations, arrangements. There were two methods that I taught you for this. One was this, in which we move this one single box to those places. And the other was in which we consider that one big box along with the other boxes, and we find the arrangement of those boxes like this. Okay, I'm using this other method because a lot of times when there's some condition applied on the inner boxes, this method becomes a bit more complicated. Although in this case, I think we can do it that way as well. I'll show you how to do it both ways, but I'm using the other method for now, this one. Let me go back there and explain that again. So we've got this one big box, 2, 3, 4, 5, 6, 7. We've got 7 boxes, 7 big boxes. Okay. 7 factorial divided by 2 factorial for those repeated letters. So now we have arranged these remaining letters. We've arranged them. Okay. Now the problem is, which 2 letters are going to come in these positions? Which 2 letters are going to come in these 2 positions? That's the question now. How many letters do we have remaining? We know for sure C is going to come in one of these 2 places. C is going to come in one of these 2 places. What about the other letter? The other letter could be any one of the remaining 7 letters. The other letter could be any one of the remaining 7 letters. So we could say from the remaining 7 letters, we could have any one of them in this position. Okay, we could do 7C1. Although in this case, since we have E's there, we could say 7 for that. Let me think about it. If we do 7 here, we have already handled for repetitions of those repeated letters. Yeah, okay, so repetitions are already handled. So we could say we've got C there already. From the remaining 7 letters, we need to select one. That will be 7C1. Or you could say 7P1 as well. It's just 7. So one of those remaining letters, that's going to come here as well. Whatever that letter is, let's call that letter, I don't know, X. Then we have to arrange these 2 letters in these 2 places as well. In how many ways can we do that? 2 factorial. We multiply that by 2 factorial for the arrangements of these 2 letters as well. And that will give us some result. You can see what that is. 7C1 makes more sense actually more than P1. The reason for that is we are arranging 2 by using 2 factorial afterwards in any case. So 7C1 is basically selecting one out of these remaining letters, that which other letter should come in this position. For that, we're using 7C1. You could just say 7 as well, and that will be fine as well. Okay. Now, this is one way of approaching this. You'll get some result from this. If we do it using the other way that we're used to doing before, let's do it using the other way. Yes, we don't have to arrange S. We don't have to arrange S, Shahryar, because they're both identical, right? So their arrangements do not matter. They're both identical, right? This 2 factorial is for arranging these two letters. The two letters that come between the two S's in these positions. That's for this. X I'm using to represent whatever remaining letter comes in that position. Okay? That gives you 5880. Ajay, let me try using the other method that we use for this as well and see if that would work in this case as well. I think that should work. There's no problem with that as well. Let's just copy that diagram. Let's do it the other way that we used to do for such problems. Achha, the other method that we used to do for this was we used to say this big box, it could come in different positions. It could remain in its current position, or it could go here, or here, or here. These could be the other possible positions. For that big box, how many possible positions are these? One, it's in its original position, and then six other positions. That becomes seven positions in total. So for this one big box, we've got seven possible positions. And then we used to say, for the remaining boxes, we can say the number of ways of arranging them. But here we've got a problem. And that problem is C cannot come in the boxes on the right side. There's a condition on C. C can only come in one of these two boxes, right? So we could think of it like this. We could say, we'll have to break it into two parts as well in this case. We have figured out how to arrange this. For the remaining six boxes on the right side, we would need to arrange those separately. And these two would have to be arranged separately because of that condition. We cannot do them together like we used to do earlier. For example, if we have 8 remaining letters and 8 remaining boxes, we used to do 8 factorial earlier, divided by whatever the repetitions were. In this case, we can't do that. In this case, we cannot do that. The reason for that is C has to be in this position. Okay? So since C has to be in this position, we could break it down. We could say, let's arrange these 6 letters separately. In how many ways can we do that? 6 factorial. Then what about these two places? One of these letters is going to be C. And then what about the other letter? There are 7 options for that from these letters. So we multiply by 7 or 7C1 for that reason. And then we could arrange these two letters as well, whatever is the other letter that comes in this position. Their arrangements, they're again going to be 2 factorial. And then since we have not handled for repetitions, we divide the whole thing by the repeated letters as well, which are 2 factorial and 3 factorial. You get the same result eventually because all we have done here is we have just broken down 7 factorial into 7 into 6 factorial, and that will give you the same result as well. We could also make cases, yes. We could also make cases, yes. Cases would be, you could say C could either come in this position. You could arrange the remaining letters, 7 factorial divided by that. That will be one case. Another possible case would be that C comes in this position, and then you arrange the other letters. Add those two cases, and that will also give you the result. That's also possible. That should also work, if that's what you're saying. Why 6 factorial? 6 factorial is for these black boxes that I have on the right side. We have to arrange them separately because in the middle boxes, we have a condition that C has to be in one of these two boxes. So there's a condition on that. So we have to arrange them separately and these separately for that reason. Is that okay? What if we do 7 factorial after fixing the C and then multiply by 7 because 7 ways to arrange the box and then multiply by 2 to account for. Yes, that should work. Logically, that should work. So that's what I was saying. If you make two cases for C, make one case for C that it is in this position. And then for the remaining letters, you do 7 factorial divided by 2 factorial and 3 factorial. And then you take another case in which you put C in this position. And that will give you the same result. You add those two up, you should get the same answer from that as well. That should work as well, yes. Is that okay, Fatima? What if we had more C's and we had to put only one in the big box? We just divide by the repetition. Okay, so the question is, what if there was more than one C and we just had to put one of them in these two places? Now, if that was the case, C's are identical. So let's suppose there were three C's. If one C comes here, then we have two remaining C's. When we do 6 factorial here, you would have to divide by another 2 factorial because of this. That's the only thing that changes there. Is that okay? If it's total 2 C's, then it doesn't matter. You only have 1 C outside. Since you're arranging 6 factorial separately, you know for sure that there's no repeated C in these positions. You don't have to divide by that. Okay. Makes sense, right? My other screen has turned off, so you might see my cursor moving on this now. Let me see if I can make that work. Just move this to the other screen. Can somebody please confirm if you can still see my screen? Can you guys still see my screen? Okay, all right. Ajana, oh, there are two more parts. Wow. Okay. How many different arrangements are there of the 10 letters in this word in which there is an S in the beginning and S at the end, and the three E's are not all next to each other? Not all next to each other. That's total minus together, right? Total minus together. Not all of them have to be together, but two can be together. That's allowed. So it's total minus together. Now, one S has to be in the beginning, another S has to be at the end. So the S's are fixed. The S's are fixed. We cannot do anything to them. We only have 8 remaining letters now in the middle. Right? We've got 8 remaining letters in the middle. For those 8 letters now, we could say what's the total number of possible arrangements for the remaining letters? There are 3 E's in them and there are 2 L's in them. So that will be 8 factorial divided by 2 factorial and 3 factorial. That's the total number of arrangements. That's the total arrangements without any condition. Subtract from this the arrangements in which all e's are together. All e's together. What would that be? You put the e's in one single box. E, E, E. How many remaining boxes would you have left? There were 8 initially, right? You have 5 others. So in total, it becomes 6 boxes, right? There were 8 initially. We merged 3 boxes and put 3 e's in them. What's the total number of boxes that we've got now? 6 factorial. 6 boxes. We can arrange them in 6 factorial ways. But some of those boxes have L's in them, right? There are 2 L's in them, and the other letters are Y, C, and H, which are different. We have to divide this 6 factorial by 2 factorial because the 2 L's are identical. These will be the number of arrangements in which all E's are together. Okay? We don't have to divide by 3 factorial because we're not considering the arrangements for E's at all. They are identical. We did not consider them in 6 factorial. We just considered this as one single box. So that's the number of arrangements in which all E's are together. You find this difference and that will give you the result. 3360 minus 360. And that gives us 3000. And that's the final answer. Okay. Dashes and stars method in this case is not going to work because of what they're saying in the question. They're saying the 3 E's are not all next to each other. When they say they are not all next to each other, that means we are allowed this case in which 2 E's are together and 1 E is separated. If you use dashes and stars method, that will separate all E's. This case would also be eliminated there. We don't want to eliminate that case. Right? It's the not all case. If they said none of the 3 A's should be together, in that case, we would use the dashes and stars method. Okay? Yes, so when they fix something and there's only one possible position for that, like in this case, S, we know that that is fixed, one on the left side, one on the right side, they cannot move. So when we consider number of possible arrangements, since S cannot even move, there is no possible arrangement for that. If there were 3S, there are a lot of conditional questions today. So you guys are thinking, that's good. If you had 3S, you fix 2 of them on the sides. Now, we don't care about them. There will just be one additional S in the middle that will be counted as one additional letter. So now, right now we've got 6 boxes, we'd have 7 boxes in that case. Right? But the S's that are fixed on the sides, they will remain there. Since the S's are identical, it does not matter which S is on the left side, which S is on the right side. It does not matter. So we don't care about their arrangements. Is that okay? No problems? Okay, all right. Let's look at the last part. जी मूसा आजकल थोड़ा सा मेहरबान है वो हमारे पे जल्दी आ जाती है आई थिंक 5 letters are selected at random from the 10 letters in the same word ये word खत्म ही नहीं हो रहा find the probability that these 5 letters include the threes okay now we are talking about selection and we have combinations involved and they're identical letters. Remember the condition for this? When we have identical letters and we are finding probability and we have combinations, we need to consider all letters as different, right? All letters need to be considered different. Okay? Okay, now what about this? 5 letters include the 3 E's. We have to make cases for the repeated letters. We need to make cases for the repeated letters. There are two S. Let's write that down. There are two S's. And then there are two L's. And there are 3 E's. We need to make cases for the repeated letters like this. Then what are the remaining letters? What are the remaining letters? 2, 2, 3, that's 7. There are 10 letters in total. That means we have 3 remaining letters. Let's combine them, consider them X. So by X, I'm representing the non-repeated letters, okay? There are 3 in number. Now, what is it that we're looking for? 5 letters are selected out of 10 letters in total. So the denominator is going to be, denominator of this probability, that is just going to be 10C2, okay? 10C5, sorry. Because remember, we're considering all letters as different. We're finding probability. That's what you need to remember for this. We consider all letters different for finding probability. Okay. All right. Now, what are the cases that satisfy the condition? They are saying find the probability that these 5 letters include the 3 E's. So all 3 E's have to be there. So 3 E's have to be there. For the remaining for the remaining 2 letters now, we have these options. What are the possible cases that we could have for that? If the 3 E's are all there, there's no condition on the other letters. There's no condition on the other letters. That will be too many cases. Okay, let's start writing them down. 0, 0, 2. This could be one possibility. With this 3, we could have 0, 1, 1. Okay, it's probably not too many. 0, 2, 0. So with 0 S's, we have these cases. Then with 1 S, we can have 0 L and 1 remaining letter. With 1, we can have 1 L and no other letter. With 2S, then we can have 0, 3, 0. These are the different cases that we end up getting from this. Okay. It's only 3 marks. There might be a slightly more efficient way of doing this. The 3 letters are already selected. Seven C2. Actually, yes, you're right. Because we're considering all letters as different, right? We're considering all letters as different. So we don't really care about those cases. You're actually right. Since we're considering all letters as different, and we know that out of 5, 3 have to be E's. So from the remaining 7 letters, we have to select 2 more, That's actually right. We do not need to make cases here. We could do it directly as well. If they had asked us for number of selections, in that case, we would not have to select, we would not be considering the repeated letters different. We would have to make cases for that. But in this case, since the remaining letters are all different, we could say from the remaining 7 letters, from the remaining 7 letters, just select 2. So that will be 7C2. And that will give you something. What's the value of 7C2? What's the value of 7C2? 21. 7C2 is 21. What about probability? 21 over this number, and that will give you the result. You can see what that is. 21 divided by 252. And that's your final answer. 1 over 12, that simplifies to 1 over 12. If you do make all of those cases, yes, you get the same result eventually, but that will be a lot of work. You do get the same result from that as well. That should work as well. Why 7C2? Okay, let me repeat. There are 10 letters in total. Remember, when we are finding probability, we consider all letters as different. When we are finding probability, all letters are considered different. Now, if we want to select all 3 E's, if we want to select all 3 E's, what we are saying is, let's write it down like this. We have some letters that are E's and some letters that are not E's. E's are 3 in total and not E's are 7 in total. Out of the 3 E's, we want all of them. Out of the remaining 7 letters, we want 2. So what we're basically saying is, from the 3 E's, select all, that's 3C3. And from the 7 remaining letters, select 2, 7C2. 3C3 is just 1. 7C2 is 21. So that gives you 21. That's the number of cases in which you have all 3 E's selected. That's a numerator divided by 10C5. You could make cases as well. But that's not required in this case. Since we are considering all letters as different, we could do it directly as well. Cases are required because the combination function does not work with repetitions, right? Combination function does not work when you have identical letters. That is why we make cases in the first place. But if we are considering all letters as different, we could just do it in one single go as well. Okay. Rita, I'll answer that at the end, inshallah. Let me quickly answer this question. 3 out of 10. Achha. So there's another suggestion. You're saying if we do 3 out of 10 into 2 out of 9 into 1 out of 8 for the 3 E's, okay, and then the remaining non-E's, which are going to be 7 out of 7 and 6 out of 6. You're saying, why does this not work? You're thinking of this like a tree diagram, right? That the first time you select a letter, it's either an E or not an E. And the next time again, E or not E, E or not E. The problem is, there are many paths like this. You're considering one possible path. E, 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 not E, not E. How many possible paths like this exist? How many possible paths like this exist? You'll have to multiply this by, you'll have to multiply this by 5 factorial divided by 3 factorial into 2 factorial as well. And then it'll work. Okay. This will be the number of paths on the tree diagram in which you have 3 E's and 2 non-E's. You have to multiply by this as well. Is that okay, Fatima? Hopefully, we can end early today, inshallah. A darts club has 12 members made up of 7 men and 5 women. Every Monday, a team of 4 is chosen at random to represent the club in a competition. Find the probability on a particular Monday that on a particular Monday, the team consists of 1 man and 3 women. Okay, we need to find the probability that the team consists of 1 man and 3 women. The team is selected randomly from these 12 members. If there was no condition, what would be the what would be the total number of possible selections if there was no condition? Out of 12, select 4 people. That will be 12, 3, 4. That's what the denominator would be. And then in the numerator, we would have the number of possible selections where this condition is met. So out of 7 men, we want 1. And out of 3 women, we want, sorry, out of 5 women, we want 3. So that's 5, 3, 3. That's what the numerator is. And that will give you the result. You can see what that is. Okay. (14/99). That's the result that we get. 14/99. No problems. 5C. Okay, we'll talk about that. Let's do this question and then remind me after this. We will do 5C as well, inshallah. Okay, can everyone please focus now? Can everyone please focus? It's an important question. You need to make sure that you understand it well. All right, question number 6 party, we're done with this, okay? Achha. Let's look at the next part now. Let's look at the next part. Every Tuesday now, the darts club chooses 3 teams of 4. Each team enters a competition in a different town. In how many different ways can the teams be chosen if there are no restrictions? There are 12 people in total. We want to select 3 teams of 4. So we can say 12C4 for the first 4-member team. And then we're left with 8 people. Select 4 more from the remaining 8 people. And then from the remaining 4 people, select 4. And that will give you the result. 34650. That's the final result that we get. Do we divide by 3 factorial? Do we divide by 3 factorial? Or do we not divide by 3 factorial? Adil, have you ever seen 7 identical males, 7 identical people? Do we divide by 3 factorial or not? Do we divide by 3 factorial? Remember that case where we discussed this? S1, where did that go? S1 permutations and combination. combinations. When we do combinations, we talk about this. When we're making groups of people. So for example, if we have 9 people who need to be divided into a group of 4, a group of 3, a group of 2, how would we do that? We would say out of 9, let's make a group of 4 first, 9C4. How many people are we left with then? Once 4 people are already selected, we're left with 5 people. So we do 5C3 for the next group. So we have the next group of 3. Once we have selected that as well, we're left with 2 people. From those 2 people, select 2 for this last group, and that gives you 1260. And that's how you can make groups. However, if you have something like this, you have 8 children, you want to divide them into 2 groups of 3 and 1 group of 2. When you have groups of same size, okay, just give me a second. Okay, sorry about that. Acha. Now, in this case, we have 8 children who need to be divided into groups of 3, 2 groups of 3 and 1 group of 2. We could say 8C3 for the first 3-member group, and then out of the remaining 5 people, select 3 more, and then out of the remaining 2 people, select 2. But in this case, we have 2 groups of the same size. Okay? We've got 2 groups of the same size. The problem here is when we have groups of the same size, let's consider this scenario. You have one grouping ABC. So we have 8 people. I'm calling them A, B, C, D, E, F, G, H. One group is ABC, another group is D, E, F, and another group is G, H. Another possible grouping could be D, E, F, A, B, C, G, H. Is there any difference between these 2 sets of groups? It's just that in the second case, D, E, F group is written first and A, B, C is written second, but groupings are the same, right? It's the same 3 ways of dividing those 8 people. It's the same way to divide those 8 people in these 3 groups. We have one group of ABC. We had the same thing in the other case as well. One group of DEF and one group of GH. There's no difference between them. So these cases are going to be double counted here. So to get rid of that double counting, we divide by 2 factorial. Why 2 factorial? That's the number of different ways we can arrange these groups. Since the arrangements of these groups do not matter, we need to divide by 2 factorial. This problem happens when you have groups of same size. So we have to divide by 2 factorial in this case as well. In the previous case, all groups were different size. Group of 4, group of 3, group of 2. We did not have that problem there. When we have groups of the same size, whatever the number of groups is that are of the same size, 2 groups of the same size, we have to divide by the factorial of that. Now, this problem is not there in this particular example. And the reason for that is this last thing that they have mentioned here. Each team enters a competition in a different town. What that means is, if you have a grouping like this, A, B, C, D, E, F, G, H, I, J, K, L. Now this grouping is different from E, F, G, H, A, B, C, D, I, J, K, L. These are going to be considered different groupings. The reason for that is, the reason for that is, each team is entering a competition in a different town. So if they were split the same way, but going in different towns, so the first group is going to town 1, the second group is going to town 2, the third group is going to town 3, then this grouping and this grouping, they would be different. If they had not mentioned this condition, we would have needed to divide by 3 factorial as well. Is that okay? Does that make sense to everyone? So generally, when we have groups of the same size, we have to divide by factorial of that. And I told you the reason for that. But in this case, they specified that each team is going to a different town. For that reason, we do not need to divide by 3 factorial. Okay, otherwise we would have done that if they had not given this condition. All right. Okay, let's move on to the next part now. In how many different ways can the teams be chosen if each team must contain at least one man and at least one woman? Okay. Each team must contain. So there are, how many teams are we selecting? 3 teams of 4 people. Let's write it down like this. We have 3 teams. Team 1, Team 2, Team 3. These are 3 possible teams that we have got. All of them have 4 members. At least one, there should be at least one man and there should be at least one woman. That's a condition for each group that we've got. What's the total number of men and women? We've got 7 men and 5 women. Right? 7 men and 5 women. Okay, now how can we break them and how can we divide them into these groups such that the condition is met, at least one man in each team and at least one woman in each team? Okay, team 1. One possibility could be that we have 3, or let's start with the smallest, right? One man. If we had one man and 3 women in this team 1, then what could be the possibilities with one man for the other teams? We could have 3 men, 1 woman. Since let's start with 1 as well here. So we do it in order. 1 man, 3 women, 1 man, 3 women. With these, in the last case, can we do 3 men? No, we can't have 3 women. That's not possible because the total number of women is 5, right? So we can't exceed that. So 1 woman, 3 women is not, 1 man and 3 women is not possible there. Achha. With team 1 having this, the second team could have 2 men and 2 women. But then the problem would be the last team would not have any women left to choose from because there are 5 of them. If 3 are in the first team, then to satisfy that condition of at least 1 woman in each team, the other teams need to have 1 woman each. So this is one possible scenario that we get then. 3 men, 1 woman, and 3 men, 3 men, 1 woman. Okay? Acha. Then for team 1, we could have 2 men and 2 women. What if we have that? We could have 1 man and 3 women here. But if we do that, we are not left with any women for the last team. So that would not work. We could have 2 men and 2 women, and that might work because then we could have one woman in the last team now, and then three men. And that works. That's another way to divide the men and the women. With two men and two women, is there any other possibility? With two men and three women? With two men and two women? Can you think of another possibility with that? With two men and two women, the second team, we already ruled out one man. What if they have three men and one woman? That is possible. And then the last could have two men and one woman. This is another possible scenario. Two men, two women, three men, one woman, and two men, one woman. Let's actually check this again. Is this possible? Two, three, two, and two, one, one. No, that's not possible. The last has to be two, right? Two, two. Yeah. Two men, two women, two men, two women, three men, one woman. And it turns out it's actually the same case as before. Just the teams are different. So one team has two women, two men, two women. Another team has two men and two women, and another team has three men and one woman. So these are the same arrangement. We can actually do them with arrangements. So this is the only unique case that we're getting with two men and two women. If we have three men and one woman, with that, we could have three men and one woman here, and one man and three women here. That is also already there. Three men, one woman, three men, one woman, one man, three men. Okay, so basically what it turns out is we only have these two unique cases. We only have these two unique cases. One possibility is that one of the three teams has one man and three women. Another has three men and another has three men. And another possibility is two men, two women in one team. Another team has two men and two women. And then the third team has three men and one woman. Now, we could just shuffle them around. We can just shuffle them around that in one case, this goes to this team two, and these people go to team one. That's another possible case. How many possible cases do we get in this case? The number of possible arrangements that we've got. How many ways can we arrange these three teams? One man, three women, three men, one woman, three men, one woman. You see, two of them are identical. This one and the last one are identical. In how many ways can we arrange them? We can arrange them in 3 factorial, but two are identical, 2 factorial ways. So we would have three cases like this. We would have three cases like this. And similarly, here as well, you have two cases that are identical, two teams that are kind of identical, two men, two women, two women, two men, two women. So we would have 3 factorial over 2 factorial cases like this as well. Now, one idea could be that you list all of those cases down. You can do that, but that will be too many cases, right? That will be 6 cases in total. You can list all of them down if you want. That's okay. Or you could just list these 2 cases down, and then you would say there will be 3 factorial over 2 factorial cases like this, and similarly 3 factorial over 2 factorial cases like this. So for the first case, we get how many cases? 3 cases like this. And the second case as well, we get 3 possible cases like this. Now, what about the number of combinations now? For the first case, we need to divide the teams now. Why we divide them by 2 factorial? Because two groupings are identical, right? Two groupings are identical. In the first case, you have one man, three women. That is a unique case, but the other two, they are the same. Three men, one woman, three men, one woman. So if you were to arrange them, two of those Groupings are identical, so we divide by 2 factorial for that reason. Okay. Achha. Now, what about the first case now? How do you figure this out? In the first case now, out of 7 men for the first team, we could say we want to select 1, and out of 5 women, we want to select 3. So 7C1 into 5C3. That's what we get there for team 1. And then what about team 2? Multiply this by 7C3. Out of 7 men, we want 3. And out of 5 women, we want 1, 5C1. This is for team 1, this is for team 2. And then team 3, out of 7 men, again, we want 3. And out of 5 women, we want 1. That's your first case. In how many ways can we arrange this? 3 factorial over 2 factorial. So we multiply this by 3 factorial over 2 factorial. And that will give you something. Do the same thing here. Out of 7 men, we want 2. So that's 7C2. And out of 5 women, we want 2. That will be 5C2. Then for the second team, out of 7 men, we want 2. And out of 5 women, we want 2. That will be 5C2. And then the third case, out of 7 men, we want 3. And out of 5 women, we want 1. And multiply this by 3 factorial over 2 factorial. That's 3 marks for some reason. You'll get something from here, you get something from here. It's either the first case or the second case. We add both of them up, and that is going to give you the result. Won't we reduce the number each time? Yes, I'm sorry about that. We should have reduced the number each time. So once we have already selected, with these numbers on top, they need to be different. These are not correct. They had to be reduced. Okay. Once we've already selected 1 man in the first case, then we are left with 6 men here. Then these 3 are also selected. We are left with 3 in the next step. Okay. When we have selected 3 women already, then we are left with just 2. So that's 2C1. And then in the next step, we are left with just 1 more. Here as well, 7C2. After that, we have 5C2, and then we have 3C3. For women as well, 5C2 and then 3C2, and then 1C1. And that will give you the result. Okay, evaluate both of them, see what you get from that. The first one is 8,400. The first one is 8,400. The second one is 18,900. And that will give you the result, which is 27,300. They wanted us the number of ways, right? So that's 27,300. That was quite tricky. 3 marks was not justified for this, as in it should have been more. That's what we do. Okay. There might be some other efficient way of doing this as well, but this is the standard way we deal with such problems, right? Making cases like these. Okay. All right, this is part C, question number 6. We have another part. We still have another part. The 7 men stand in a line for a photograph. Now this looks easy now. 2 of them are brothers, George and Harry. How many different arrangements are there out of the 7 men, in which there are exactly 2 men between George and Harry? Now that's a standard question now in the recent papers. How do we approach this? We've got 7 men in total. Let's make 7 boxes for that. There are 2 men, exactly 2 men between George and Harry, so we can make a big box that has 4 small boxes inside, like this. We have this big box that has 4 small boxes. Okay. At the end of this box, on one side we would have G, on another side we would have H. They can switch places with each other as well, right? What's the number of arrangements that are possible now? George and Harry, they can switch places. In how many ways can they switch places with each other? 2 factorial or just 2? Okay. Then how many possible positions do we have for this red box? It could stay in its current position. It could go here, it could go here, it could go here. That's 4 possible positions. So we multiply this by 4 as well. Okay, 2 factorial was for G and H. And that's what 2 factorial was for. And then 4 for the possible positions of that red box. And then how many people are we left with? 5 remaining people. They are supposed to be placed in these 5 remaining places. 5 people, 5 places, and how many ways can we do that? 5 factorial multiplied by 5 factorial. And that will give you the result. Okay. 960. And that's your final answer. Achha, let's move on. Last question, permutation combination. That looks like a long one. Aliza has 10 different books from the series Squares and Circles. The books look similar except for their color. There are 3 blue books, 2 red books, 2 yellow books, one or then that's a lot of books. 10 different books, and we've got all of them. Okay. 3, 2, 2, 1, 1. That's 6 different colors. She places the books in a row on her shelf. She's only interested in the arrangement of the colors, mashallah. She's only interested in colors. She does not have anything to do with whatever is inside those books. She wants to arrange them using colors. How many different color arrangements are there of the 10 books? How many different color arrangements are there in the 10 books? What do you think? How many, how many color arrangements are there? 10 factorial? 10 factorial? The books are all different. So if we were to arrange the books, we would say that's 10 factorial. But she's only interested in the color arrangements. So for example, if you have blue book, the first blue book and the second blue book together like this, then she doesn't care if it's B1, B2 or B2, B1. They mean the same thing for her. So books of the same color, in this part, we're going to consider them identical, right? There's no difference between them. So we divide by 3 factorial because of the 3 blue books, because their arrangements don't matter, right? And then also divide by 2 factorial because of the red books. And then also divide by 2 factorial because of the yellow books. Okay. And that will give you the result and see what that is. What do we get? 151,200. That's our final answer. Okay, that's the first part. We're only arranging the colors. Because we still have 10 books, right? We still have 10 books. We are arranging 10 books. If you only if you only do 6 factorial, that does not account for this possibility that you have, for example, blue, red, and then a blue book. Because then you can't have this possibility, right? Blue, red, blue. That's also possible. That's a different color arrangement. Okay. All right. Now it says how many different color arrangements are there of the 10 books in which the 3 blue books are together, but the Two yellow books are not next to each other. Now, again, we're talking about color arrangements, which means books of the same color are identical. That's the assumption. Books of the same color, we consider them identical. Now, what's the number of books? Let me just write that down here. Three blue, two red, two yellow, one orange, one purple, one green. Now, the three blue books need to be together, but the yellow books should not be together. That's a standard case that we do when we do arrangements, right? Some objects need to be together, some other objects need to be separated. What are the objects that need to be separated? The yellow books. Let's write them separately, and then the rest of them, the other books. How many are there? 8 books. What we can do is we can use dashes and stars method, where we can make 8 dashes initially for the remaining books. 1, 2, 3, 4, 5, 6, 7, and 8. For non-yellow books, we make 8 dashes like this. And then yellow could come in the places between them that will separate the yellow books. So that is the condition for yellow books. But then they're saying the 3 blue books need to be together. So out of these 8 books that we've got, 3 need to be together. So what we do is we merge 3 dashes. We merge 3 dashes and we make one big dash here like this, in which we put the 3 blue books, B, B, B. And then the rest of them, they are going to be R, R, Y, Y. No, Y is not here. O, P, and G. Right? These are the other books, remaining books. Now the yellow books that should not be next to each other, they can come in the gaps between them now. These are the possible positions of the yellow books. Okay. In how many ways can we arrange this now? How many dashes do we have? 1, 2, 3, 4, 5, 6, 7. We've got 7 or 6. 6 dashes. We've got 6 dashes. In how many ways can we arrange these 6 dashes? 6 factorial. But then some of them are identical. These 2 dashes, they're identical, the 2 red ones. So we divide by 2 factorial because of that. The others are all different. So 6 factorial divided by 2 factorial for this reason. Okay. Then what about the yellow books? There are 2 yellow books. How many possible positions do we have for them? 1, 2, 3, 4, 5, 6, 7. There are 7 stars. There are 7 possible positions for the yellow books. In how many ways can we arrange those yellow books here? 7p2, but then both of them are identical. So we divide by 2 factorial because of that. This thing is equivalent to 7c2. So you can also use 7c2 in place of 7p2 over 2 factorial. That will also work. And that should give you the result. You can see what that is. Makes sense, right? 7560. That's your final answer. ठीक है. No issues with this? Do we move on? Why are we dividing 6 factorial by 2 factorial? Because of these 2 r's. There are 2 dashes that have r's on them, right? So this 2 factorial is because of those 2 r's. Okay. Okay, now some of you are saying, why are we not multiplying by 3 factorial? Because we also have to arrange the blue books. And then some of you are saying, why are we not dividing by 3 factorial? Because they're all identical, so we divide by 3 factorial. Do we multiply by 3 factorial or we divide by 3 factorial? Do we multiply by 3 factorial or divide by 3 factorial? We don't do any of that. Or both, yeah, or both. So that's a good point. You do both or none. In how many ways can we arrange these three books? The blue books, you can say 3 factorial, but then all of them are identical. So we divide by 3 factorial. They get cancelled out. So it doesn't matter if we arrange them or not. Identical objects, their arrangements do not matter. Right? So even if we do that, they get cancelled out. Okay. We cannot just divide by 3 factorial because these are identical, because we are not considering their arrangements in the first place. We did not multiply by 3 factorial in the first place. If we had multiplied by 3 factorial, only then we would divide by the repetitions like this. Otherwise, we won't. Right? Musa, that is not going to make me end the class early. Can we use combinations? Can we use combinations? Uh, we're talking about arrangements, right? We're talking about arrangements. Why would you use combinations here? Combinations, I only said in response to somebody who said in the chat, this thing, this is equivalent to 7C2. 7P2 over 2 factorial, you could replace this with 7C2 as well. The reason for that is the yellow books were considered identical. So we could just think of it like this. We've got 7 places and we have to select 2 places where we can place the 2 yellow books because their arrangements don't matter. They're identical. So in that case, instead of this, we could use 7C2 as well. Okay. But I think for most people, this is going to make more sense. Since we're arranging, we use permutations. But then since they're identical, we divide by 2 factorial because of that. Okay. I hope that answers the question, yeah. Right, okay. So let's be quick and do these last 2 parts. It's getting late now. How many different color arrangements are there of the 10 books with exactly 4 books between the 2 yellow books? Another standard case that we do, right? Again, we're talking about color arrangements. So books of the same color, they're considered identical. What we can do is we can make boxes. Make boxes like this. There are 10 books in total. There are 10 books in total. We could say we have 10 places for them. We've got 10 places for them. Achha. Now, what we want is exactly 4 books between the 2 yellow books. So that makes it 6 books in total, right? So we have a big box that has 6 books in it. Let's make it like this. We have this big box that has 6 books in it. Okay. Achha. Now, at the ends of this box, we have the 2 yellow books. We've got 1 yellow book here, another yellow book here at the 2 ends. The other books are 3 blue. So we've got B, 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 and red, red, yellow, yellow, red, red, and the other 3 are different. OPG. These are the remaining books. Books of the same color, we're considering them identical, right? Achha. In how many ways can we arrange them now? There are multiple ways that we did for this, right? One possibility is we could say, let's start with this box, the red box. It could either be in its current position Or it could be here, or here, or here, or here. So how many possible positions do we have for this big box? It could either stay in its current position, second position, third, fourth, fifth. There are five possible positions of the red box. That's not 5 factorial. That is just 5. That's not 5 factorial. It's one box that we are arranging. There are five possible places for that box. One box, five possible places. That's just five. If we have five objects and five places, that is 5 factorial. This is 5p1. Yeah, this is 5p1. That's just 5. Because you're talking about only one box and five possible places. So the red box that can have these five possible positions. Okay, now we've got these places for the other books. How many places do we have? 1, 2, 3, 4, 5, 6, 7, 8, right? We can arrange them in 8 factorial ways. The remaining books in those 8 places, 8 books, 8 places, that's 8 factorial. But then some of them are identical. The blue ones are identical, we divide by 3 factorial because of that. The red ones are identical, we divide by 2 factorial because of that. And that's going to give us the result. You can see what that is. Okay. This gets repeated in recent papers again and again. Make sure that you understand this well. If you are not sure about this, post in the group and I'll share with you a video on this in which we cover multiple methods of approaching these problems. Okay, post that in the group and I'll do that inshallah. Or maybe somebody else in the crash course can share that video with you as well in case they can do it quicker. Okay, last part. Alisa selects 4 books from her 10 different books from the series Squares and Circles. Find the number of different selections if the 4 books include at least one red book, at most one blue book, and exactly one yellow book. Okay. Now, what was the number of blue books? We had 3 blue books in total. There were 2 red books, and there were also 2 of another yellow books. 2 yellow books. These were the colors that were coming multiple times, and then the rest of the 3 colors, they were only coming once. We can write them together. The remaining colors were OPG. So there are 3 of those remaining colors. Achha, now what's the condition? At least one red book, at most one blue book, and exactly one yellow book. Okay, yellow has to be just one. This number is fixed. And she's selecting 4 books in total. Now, what are the possibilities? Satisfying those conditions? Let's actually write them in order. Red, so it will become easier to read those conditions and fill these. Red, blue, and yellow. Okay, that's the order that in which they have given the conditions. At least one red. So one red, at most one blue. So the minimum, firstly, write the minimum possible values for all of them. What's the minimum possible value of R? 1. Minimum possible value of blue? 0. Possible value for yellow, that's only 1. With 1, 0, 1, the rest of the books, they have to be 2 in number. Okay, now keeping red fixed at 1, blue could be 1, yellow has to be 1, and then 1 from remaining. So these are all the cases where we can have one red book. What if we have 2 red books? With 2 red books, we can have 0 blue, and then 1 yellow, and 1 other. And then with 2 red books, we could have 1 blue, 1 yellow, and 0 other. These are the cases that we get. Right? These are the only 4 cases that we're getting from this. Makes sense, right? In how many ways can we do this now? Out of the 2 red books, So they've done something weird here. In the previous part, they were talking about color arrangements. They were talking about color arrangements in the previous part. They're not talking about colors anymore. They're not talking about colors anymore. They're talking about 10 different books. They've not mentioned colors even once here. And they've clearly mentioned we're talking about 10 different books. She's selecting 4 books from 10 different books. Colors don't matter now. As in books of the same color, we don't consider them identical anymore. Because earlier they were mentioning color arrangements. In that case, we were considering same colored books identical. Now they're saying 10 different books. And they've not mentioned color arrangements in this case. So all of these books are going to be considered different. Which means we're going to select from the red books as well, from the blue books as well, from the yellow books as well. Even though they are the same color, the books are different. So the first case is going to be 2C1 into 3C0 into 2C1 into 3C2. That's the first case. The second case, 2C1 into 3C1 into 2C1 into 3C1. 2C2 into 3C0 into 2C1 into 3C1. And then the final one, which is 2C2 into 3C1 into 2C1 into 3C0. These are the 4 cases that we get. Evaluate each one of them, add them up together, and that will give you the total number of different selections. The first one gives you 2 into 1 into 2 into 3, which is going to be 12. Then second one, 2 into 3, that's 6. 6 into 6 is 36. Please confirm these calculations. 2C2 is 1, 3C0 is 1, 2C1 is 2, and that is 6. 1 into 3, 3 into 2, that is 6. Okay, and that adds up to 24 plus 36, 60 for me. That's our final answer.